today's, today is today the C programming language, and using standard tools. And another big difference is it actually runs on multiprocessors. And so we'll spend quite a bit of time talking about like how to build operating system for multiprocessors, but this is it does run on multiprocessors. And so this, this is basically straight, if you will, a ripoff of Ritchie and Thompson, who wrote the early Unix operating systems or versions of Unix. Okay. A long time ago in 828, we actually used to study the original V6 source code, which runs in the PDP-11, which is a machine you probably never heard of. In fact, we made every student in this class learn PDP-11 assembly. It was very exciting. So I learned it, so it was very good. So to make your life easier, we wrote one that actually runs on the x86, so that it's exactly the same assembly that you're using in the labs, and it's a modern processor that everybody uses, and you should know x86 anyway. And so this is now all standard. Okay. But in many ways, it's just exactly the same. The code is even. There was a guy, Lyons, who unfortunately passed away a couple of years ago, who wrote a little commentary that went along with V6, and actually got quite famous. And the commentary and the source code, the commentary came with a typeset source code, and the source code is exactly, this source code, XV6, is exactly typeset as Lyons did it, including the sheet numbers, and every line has a line number. You will notice that they're very carefully typeset so that the first 2 digits of the 4 digits actually is a sheet number that corresponds to the page number, and so you can easily and quickly find code. Okay. So what I'd like to do is, actually not really dive into the details. This is basically like how do you implement the operating system. Let's first see actually what does it provide, and the way we're going to get at that is we're going to look at a little bit about how shell works. In fact, this is what I was doing early on, where you're all very quiet looking at me. This is a message. And one of the inventions of Unix, as we will see, is Unix actually separated the shell from the operating system. The shell is nothing else than the normal user program. And you can replace it. In fact, like today, many Unixes have many, many, many different shells. Presumably you have your favorite shell, Python shell, someone want a functional like a Lisp shell. Other people have whatever, C shell, B shell, standard shells. Okay, and so one of the reason that it was possible to actually have the shell as a user program is because they chose the abstractions that the operating system very carefully. And so it's like it didn't have to be built into the operating system itself, which was sort of the standard at that time. So we're going to look a little bit about that, and then will force us to learn a lot about many of these sort of Unix key abstractions that the operating system must provide, and that you're going to be providing in your operating system you're going to be writing. In fact, the operating system you're writing is going to call it Josh, GAOS. And so XV6 stands basically for first of 6 Unix, but running on an x86. That's why it's Okay, so the core of a shell is actually a reasonable, straightforward, and I'm going to abstract a bunch of stuff away because otherwise I'll be writing too much on the board, and I don't want to look too much at the code today. But if you really care about it, on sheet 76 in the booklet, there is a complete functional, there's a functional shell that provides some features. What you might typically find in a shell. And so once in a while we'll come back to that, and you'll find out it's only, I think it's 7 or 8 pages of, 9 pages of code. Right? So it's not and you imagine this is DUI, correct, for the operating system. There's no other UI, this is it. And this is the way to interact with the computer. And so it's 8 pages of text, you can replace it, and a lot of students actually what they do is to find a project they actually replace the shell. So all the text is also on the PDF online. So and so it's helpful, at the end of the lecture today or the next couple of days, you may want to sort of browse through this code and sort of make sure that you really understand what actually shell does. And the first chapter of the text that we just posted this morning, does cover a lot of the basic, shell ideas and programs that run on the thing. So here at the end of this lecture, like, I'm very confused because this guy made it very confusing to me. Hopefully the text can help you, and if that doesn't help you, you can read the source code because that's a definite answer. Might have bugs, but it does implement a shell. Okay, so the basic structure of the shell is actually very, very straightforward. Basically, it's a while loop, just waiting for input, right? First actually prints out the prompt, then it reads the input, parses the input. I'm not going to talk about that, but most of the complexity actually in the shell is actually parsing the input. So it splits apart in basically a command and some arguments, where the command might be ls, cat, word count, you're sort of, I don't know how many people actually use Unix shells. How many people use shells actually? Good. That's good. So sort of a lot of the small ls, all the CD, all those sort of echo, cat, those standard sort of little programs. There are also usually a lot of programs that the shell can invoke, and we'll talk a little bit about it. And they're all implemented in the abstractions that we're going to be talking about right now. Okay. So the shell reads command in, let's say maybe ls. Ls is just a command, no arguments. And then the next thing it does, which is immediately an example of an interesting abstraction, it calls fork. And fork is the way in a Unix abstraction, or Unix call, system call, to actually create a new process. Right? So if you think about the machine, some space here. Think about if we did a look just for sort of an abstract view of memory, right? There's going to be some memory on the computer. The memory at least is going to contain, somewhere in the operating system. And it turns out there's an interesting question which we'll talk about next week. But let's say it sits somewhere in memory, and that's the instructions and the data structures that form the operating system. So they sit somewhere in memory, and then during, this is what happens during boot. The operating system gets loaded in memory, it starts running in memory, it creates the first process, and this is all we're going to talk about next week. And the first process, is something called /init typically, and then it creates a new, it will actually fork off, this is Unix terminology, it will fork off a shell. And so that is, we might have in this case, where we have a shell running, again, and what is in memory are the instructions of the shell, the data structures, the binary representation of the shell. It runs happily and prints the result, you try to do something, and then fork is called. And so internally, in the kernel, or in the operating system, we'll talk a lot more about that next week, there is something that's called a proc table. This is a table with processes, or active processes. And as you will see in x86, we use everywhere brain dead data structures. So we're happy to search for tables. We don't use hash tables. We don't do anything similar. There's linear. Everything is linear. And it turns out to be no problem at all. Correctly, we do 100 entries. Linear is actually pretty fast. So in general, this is not an issue. Real operating system, of course, use more advanced data structures, but that's just a question of writing some code, maybe replacing the table with a better data structure than you would in 046 or 606. So we have a proc table, and every process, there's an entry associated with the proc table. And for example, it has process ID. So what happens with fork is a fork internally will make a copy of the currently running process, the shell, somewhere in memory, and that copy is basically completely identical to the process that calls fork is called the parent, and then the process that actually being created is called the child, and it will find another, and this is hit 1, hit 2, get a new entry in the proc table, so it keeps some information about the process, and then it makes a literal copy of the process, including its stat, like everything. It's completely identical, except for one little thing. That process, both processes actually start to run in principle, and if you have two processors, they will run actually concurrently at the same time. And in one case, fork will return the value 0, and in the other process, the process will return a value bigger than 0, which is the process ID. Okay. And so the child actually, in the child case, your forward will return 0. In the parent case, the forward will return the process ID of the child that's being created. Okay? And so there's a little bit of cleverness in how to do that, but that's the abstraction. And we'll see actually how fork, later on, we'll see exactly how we do that and how fork is implemented, but that's the abstraction. Then, so that corresponds to this lines of code, and then the next thing that actually happens is that we're not running, let's say we're type ls right in the shell. What we've done so far is just create a second copy of the shell, which is not what we want. We actually want to run ls. And so there's a second system call, called exec, which actually runs, which replaces the existing image in memory for the shell with the image passed as an argument to exec, which will be named ls. And that's just a regular file that's living somewhere in the file system. Loads it in memory. Does some small fixing up, and then we'll run the first instruction of ls, started at 0. Okay. So one thing you might wonder about, like, why actually is this split, fork and exec split in 2 operations? This is like extremely wasteful, right? To like make a complete new copy, and then the next thing you do, you throw it away again. Then the third time in a second, we'll see why it actually turns out to be sort of a fortunate. This was not completely by design, but close by design. Design decision. The other way you can imagine is that like fork and exec are going to be combined in a single call that says like run /bin/ls. Now so this is the child case. The parent case, in the case of the shell, there's nothing else than waiting for the child to be finished. So there's the wait call, and when the child is actually all done, the wait call will return, and then the parent process will continue running. And so this is sort of conditional synchronization between the child and the parent. And then, of course, if the value is negative, if the gate ID is a negative number, then actually that means the convention in Unix is like everything below 0 is an error, and overturn -1, and then somewhere else there's a kernel, there's a global variable set to actually what the actual error was. And print error allows you to print that in a clean way. Okay, so that's the basic structure of the shell. And if you look in the code, that's exactly what it does. Now, there's a couple things that we need to sort of understand a little bit more. So let's first look at how does I/O happen? Right? And sort of ls, it's got to print some bunch of stuff. Right? The shell needs to print and some text to the console. And how does that happen? And, you see how that happens. You use a write system call. And it takes a couple of arguments. It takes an argument of the file descriptor, which I'll talk about in a second, and then a string, and then the length of the string. And the file descriptor here is just an integer. In this case, it's 1. And this is important because there's a convention in Unix that file descriptor 0 is actually input. So typically you read the file descriptor 0, 1 is output, and 2 is standard error. Talk about that in a second. And so what this just basically says, write to file descriptor 1, which is supposed to be standard output, this particular string. And the one thing that's important to realize here is that the shell, right, internally, doesn't really know anything about devices. It doesn't even know where it's printing to. It just prints to 1. And it turns out internally these file descriptors are used to redirect or set I/O appropriately, so that maybe it will print to the console, or maybe print to a file, or whatever file descriptor 1 it actually happens to be pointing to. But the cleverness here is that the program, the shell itself, internally doesn't need to know that. And just actually by this convention, it just prints to 1, and hopefully the right thing will happen. Because the OS will organize it. Okay. And so let's see, why these three features, file descriptors, fork and exec while they're useful. Right? And just give you, and there's a very simple example. You just immediately see that is why it works out nicely. So let's say we want to redirect, right, like in any other shell, the output. Just make sure you turn off the projector. Sorry. So let's say you want to redirect the output of ls to a file. In Unix, that's easy. Correctly type you call dollar, you type say ls big O1 10 standards in Unix convention. So that the user can do that, and it's fast, right? Because you can take the output of the program, or the file, and later add it, et cetera, et cetera, et cetera. So how do you implement that? Well, I've told you basically enough for you to modify, my amazing shell to actually support I/O redirection. So this is a good thing to think a little bit about for a second. Yeah.
So you can open temp1 and then have its file descriptor be 1 when executing the shell.
Mm-hmm. So let's see. So what we're going to do, and this is why exec and separation fork and exec is important here, is before the exec, we're going to sort of manipulate a little bit the environment of ls so that the right thing will happen. Right? We're going to insert basically some code here in case that the input wouldn't be parsed the argument that when there was a bigger sign. Right? We're going to do some additional actions. What are these additional actions? Well, the first thing we're going to do actually is we're going to close one. Basically says, I'm done with this file descriptor, I don't really need it anymore. Right. And then the next thing we're going to do, we're going to open, we need to open up the file we're going to write to. We're going to need an allocated file descriptor so that we can actually write to the file, because write takes file descriptor short, and so we need to get the file descriptor. The way you get that is using open or create. Often combined now, but maybe we're writing something like that. The semantic is bigger than is that you create a new file. Right? If temp1 already existed, then it's gone. So you're going to do create. And temp1. And so then there's an important rule. Create actually takes some more arguments, but who cares about that? Actually, one more. And there's an important rule in Unix, and that's again to make things out work nicely, that Unix will return, the operating system will return the first available file descriptor. And so, what is the first available file descriptor? 1. Right? So this MD will actually be 1. Is there anything else we need to do? No, we're done, right? Because exec will fork off ls. ls will write to file descriptor 1, and we just set it up that actually that happens to be corresponding to the file temp1, right? And everything is set up. And so where did we get that from? Well, the reason that we're going to fork and exec it separately allowed us to manipulate the environment before we run the program, right? So that is nice. Okay, so there's a second part to that, which I forgot to tell you, of course. When the child, okay, so let's do something slightly more complex. Let's say we're going to run a script. Okay, we're going to do that actually, let's only do this script. Let's say temp2. So this is what we type in on the shell, correct? So this means in Unix parlance is run, shell, this program shell itself, make it read from the file script, and put the output in the file temp1 or temp2. Right? And the script might actually, let's say, we put in, this is just an ordinary text file, correct? And we might put in the script like echo1, echo2. to print out something to the console. So echo 1 will print out 1 to the console. You'll see in the most of this class, all the examples are totally done in simple, but hopefully they'll still get the essence across why the actual operating system is called. So let's first think a little bit about, it doesn't matter if this is a shell versus LS. Do we actually have to change anything to our shell to actually run the shell as a child itself? Some version going, no, right? Because we'll fork off a second shell, then exit shell, plays it with itself, and start from the beginning, right? And so now we have basically 2 shells running, one waiting on the other. Right? And the child is a shell, the parent is a shell, the parent is waiting for the child. And what does the child do? Well, it's going to read from, I didn't show that, it basically read, or it's going to read from file descriptor 0. So this is going to work on grid, right? Because the shell itself doesn't really, this is why it's nice, but the shell doesn't really know whether it's reading from a file or from the console. It's going to read from file descriptor 0. So what do we need to do to actually implement a smaller boot redirection?
Close 0 and then open the script.
Yeah. Basically exactly the same thing as here, right? And what we'll do when we see a smaller than sign, we'll do close of 0 and then open the file, which is going to be script, and that will be file descriptor 0, and so things won't work out, right? And again, no change is really necessary to the structure of the shell. There's small extensions to actually get this all to work out. Make sense? Okay, so the shell now starts actually reading from this file script. It doesn't really know that it actually is not reading from the console, right? It's a good extraction. And so it will read echo 1, right? And so we'll interpret this echo as a command, and this is an argument, right? And run it. And it will redirect the output to temp2. The one important thing is that when echo, when the parent-child shell forks off echo, echo will inherit the file descriptors that actually the parent had. And so we remember that we had set up the child shell to actually read from script and print output to temp2. The same thing will happen with echo. That's the rule in Unix. For a child, it inherits the file descriptors of the parent. And you can see why that's a good idea, right? Because then it makes you don't have to make any changes to actually make the script work. Everything will work out fine. And echo will print 1 to the file temp2. Even though the script doesn't really know anything about it, certainly echo doesn't really know anything about this, right? Make sense? Now there's a little bit of an issue. Right? There must be some mystery, more stuff going on, because let's say we do echo 1 and we then do echo 2. What will be the output in temp2? We were like, did in the end, we do cat temp2. What do we expect to see?
One backup in 2.
Yeah, 1 in a new line for the going to event, 2, and then 2. With what I've told you so far, will that work out? Well, it might be, it might not. I've not told you enough to actually know for sure that actually will work out. Because the first funny thing to actually notice is that write actually didn't include an offset. It actually didn't say like, you should be writing at offset 10 or 2 or 0. Right? And so those are sort of unusual. Most of these system calls that will talk about different offsets. So what's going on is that there is internally in the operating system, there's sometimes called the file table. And that is all the table with all the open files. So each file that's open, there's some information stored in it. And the same file might actually show up multiple times. But one of the things that's crucial that actually has an offset. So the operating system internally maintains an offset variable. And so, and when you open a file for the first time, you set it to 0. So the operating system set to 0, moves it using LC. And so that controls where actually things will show up. And so so what's going on exactly? Well, so here we have page 1, page 2. Internally, there's a file descriptor table. that maps, whatever 0 to say an open file. And the rule is if the child inherits a file descriptor from its parent, then its entry 0 or its file descriptor entry will point to the same file entry as the parent did. Right? So they will share the offset. So the parent and the children will share the offset. So this will cause, correct, this to work out correctly. Because the first process, printing file descriptor 1, which is a shared file descriptor because the parent and child have a shared file descriptor, so it will push the offset to 4, 3 characters 1 plus the new line, and then 2 will print the next couple of characters. Okay? Make sense? So this allows us to actually run this program correctly. So you see here the sort of careful, these abstractions were clearly carefully chosen, correct? This is not a random, whatever, let's do something. There's a carefully thought out plan about what the rules are for fork, what the rules are for exec, what the rules for file descriptors are, actually the invention of file descriptors, that the offset is implicit and not part of the API. And these are all examples of sort of very careful API design to occasionally get with few mechanisms, many features. Right? So there's a good example, and this is sort of this kind of thinking you should completely sort of keep in your head while you're looking at different OS abstractions. Why did they do it this way? What does this allow you to do? And this is Shell is a great example of like how you can build a lot of interesting things with very few mechanisms. Yeah.
How does the second line return back to the original shell?
So at some point you will read the end of the file.
But it's wrapped in a while one.
Yeah, so I cheated. Because you can imagine that I cheated slightly. The read command, correct, will at some point read from file descriptor 0. If you read from file descriptor 0, you're at the end of the file, that will return 0. You know that basically you're at the end of the file. And so you can imagine that somewhere a read command actually exits this program when it runs 0. So exit is the call to terminate the process. Okay? And so that will terminate. The parent is in wait, correct? And so when the child doesn't exit, echo 1 doesn't exit, that terminates, that goes to this shell, correct, is waiting, then it will run the next command, that will actually exit, and boom, boom, and then it will wake up. Make sense? Good question. Okay, so one more sort of little thing about file descriptors to sort of show that not to bring this set up here. Let's say we want to do this ls file 1, file 2, and some non-existent file named non-existing, and we do this temp1 and then temp2. Everybody know what this does? In sort of standard Unix, whenever we were listing the free file names, correct, and send it out, it goes to temp1, standard error, and then file descriptor 2 goes to temp2. And you often want to separate the error messages from like regular input, so this is why this sort of feature in the shell exists. Is there a lot of additional mechanism necessary to actually implement 2 bigger than, redirecting standard error beyond what we already have seen? Not much, correct? Because the only thing we need to change is like instead of doing close 1, we'll do close 2, and then that's the end of the story.